Hello everybody, let's get started. Tonight we're supposed to review this logical adder subtractor circuit which is used inside processor, inside the ALU to compute integer addition and subtraction. So with that respect and with respect to any other thing, do you have any questions or topics for me to discuss tonight? In the meantime, let me go to the discussion board and see if there is anything. No, module 4 doesn't have any question from you. Okay, all right. Why don't we just start with this poll, class preparedness poll. Please take a time. You can probably do it anonymously as well. I believe so. Yeah, take a minute to participate in this poll and we'll see how the class is ready for tonight. $28 of 32 has participated. I'll wait for probably 5 more seconds to end this poll. Okay, let me share the result with you. Seems like most of you have reviewed, at least almost like 43% reviewed all of them for the lecture video, lecture notes. Other 54% said some of them. Please make sure you review all of them before coming to the class. Otherwise, discussion may be like on top of your head. Like it will, yeah, you'll not feel what's going on. You may miss important point there. About the queries, oh, you don't have any queries, or at least some people says they haven't noted on the discussion. Maybe you have question, you can ask me. What's the lab videos? Okay. Lab are very important, guys. Like you need to follow through the schedule, and it's all in your syllabus schedule as well. You see that each day I assign the lab videos and perform the experiment that you need to do. These are key to actually be successful in our project 2. Project 2 is really hard. Okay, it's nothing like project 1. Project 1 is just a baby step basically. Okay, and this is a gigantic step. So please make sure you are up with the labs and the experiment and with the projects. It's very fast-paced project. Okay. All right. Then let's see. We can start with a problem tonight. Let me share my whiteboard. And okay. Okay. The problem is something like this. We need to count the transistors in a combined 32-bit adder subtractor, which uses all NAND gate. Like it is not a, like we know the adder subtractor is mostly based on the XOR and 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 some OR logic, but it is using all NAND. Like nothing is constructed with the other gates. Everything is NAND. Now let's say each transistors then takes an average 20 nanometer by 20 nanometer area in the silicon, just in hypothetical data. How much area this adder is going to take, this 32-bit ripple curry adder, by the way, what we actually discuss in the lecture videos. How much area this is going to take, and also a little bit twist on the other side of the problem is that how many adders you can pack within a 1 millimeter by 1 millimeter square of silicon. So these adders are real electronic circuit. It can be imprinted on piece of silicon. They are, in fact, for your processor, the chipset, whatever you are using. And we need to determine how much array it takes, okay, each adder. And given, if you are given with a space of 1 millimeter square by 1 millimeter square, 1 millimeter by 1 millimeter silicon, then how many adders you can pack onto that piece of silicon. So before we going to solve this problem, let me tell you one possible minimum implementation for the XOR. XOR gate, remember, is very is used all over the place on the adder subtractor circuit. So XOR, so B is a function like A not B or A B not, which straightforward, if you want to derive, it becomes with the De Morgan, it becomes like A bar B whole bar, A B bar whole bar, right? So that means it needs, like, this is one NAND. If you want to implement with all NAND, this is another NAND. This is two. This is one NAND. This is another NAND, and this is another NAND. So total, we need 5 NANDs if we want to derive in straightforward way. However, there is one minimized XOR with a NAND. It looks like this. So this output is really A XOR B. We can kind of easily derive it, like from the circuit, the reverse derivation. It's basically your function is AB whole bar with B AB whole bar, which we can, by De Morgan, we can write it like A bar or AB, B bar or AB whole bar, which now we can do like A bar or AB whole bar or B bar or AB whole bar, okay, which is, by De Morgan, we can write AB bar whole bar, B AB bar whole bar. Wait a minute. Wait a minute. I did some step wrong probably. So A bar, let's see. This step is, okay, first of all, this is whole bar. Okay. From this to this step is correct. And from that to A bar or AB whole bar or B bar or AB whole bar is correct. Now this is also AB bar, B bar, Okay, okay, we can now further proceed like this. De Morgan, it is A bar or B bar, B, A bar or B bar. This is A bar, A B bar, A bar B, B B bar. A bar is 0, followed by A B bar, A bar B, followed by 0, which is A B bar, or A bar B, which is A XOR B. So this is the XOR implementation with a minimum number of NAND gate, which is 4. Assuming that your XOR gate has 4 NAND gate, we need to calculate number of transistors in a 32-bit adder subtractor, ripple carry adder subtractor with all NAND gate. All right, so let's solve this problem as a group, and let's take maybe about 20 minutes to do so. Let me turn on the share screen. Okay, it's turned on. Where is my breakout rooms? Here. Okay. Okay, I see there are rooms with 1 people. I will change them, but anyway, let me assign 20 minutes on this problem. And let me open. Please join in your room and solve this problem in group. Okay, let's get out of the breakout room and let's see what you have done as a study group. Let me see. Why don't I turn to study group 8? Andy, Yo, Goman, Jonathan, Sweta, do you want to share your findings of this problem?
I would say that our answer doesn't seem correct, but
What's your approach?
okay. So first we try to find out how many NAND gates are in a 32 full adders, and we got 2,400 transistors from that.
Okay, all right.
And then we added that to get our total transistors were 3,200. And then we tried to multiply that with to find the amount of area.
Okay. Can you elaborate your steps for how you came up with that 2,400?
Okay. Yeah, so we found that there were 2 XOR gates, 2 AND gates, and 1 OR gate.
Okay.
The XOR gates are made out of 5 NAND gates, and the AND gates are made out of 2 NAND gates each. The OR gates are made out of 3 NAND gates.
Okay.
So that was a total of 40 transistors for XOR gates, 20 transistors for AND gates, and 15 for OR gates.
Okay.
And then when we found the total, that was 2,400 for each 32-bit full adder.
Okay. And
yeah. So after that, we found the total area to be, hold on, 2,508,800 square nanometers.
Okay.
And that was our answer.
Your approach was correct. The answer is not matching, a little bit goofing up on this thing, but the scale of that seems to be correct. Like if you think that that big nanometer square is a big answer, it's not. It's basically very, very tiny space on the silicon. So yeah, I would say your approach is correct. And let's see what we can do. Why don't I do and see where did you actually guys make mistakes in calculation. First of all, XOR gate, as I showed, minimum 4 is not 5. Okay, well, 5 answer is also right. I'm not saying it is wrong, but let's go with the minimum XOR gate calculation and let's plug that into our calculation. So sharing my screen, and basically I have this 32-bit RCA, which, as you said, we start with, let's say this one, right? You can see my slide, right? I just bring out the slide of your lecture.
Yes.
Okay. So we start with the half adder on that. So half adder has one XOR, one AND gate, right? So let's calculate that. So half adder, one half adder is equals one XOR plus one AND, which comes down to 4 NAND plus 2 NAND, which is equal 6 NAND. And then one full adder has 2 half adder and 1 OR gate. So one full adder, you can directly add them too, but I'm just going with this circuit, half adder plus 1 OR Now 2 half adder is 12 NAND, right? 1 half adder is 6 NAND. So 2 half adder is 12 NAND plus 1 OR is 3 NAND. How so? Because like let's say A or B, we can write it down by De Morgan, A bar, B bar, whole bar. That means essentially this inner one inverter is one NAND, other is another NAND, and together it's a NAND. So 3 NAND we can use to make a OR gate. Now from here, we have for the once we have the 1-bit full adder, 32-bit ripple carry adder will have 32 of, like here this example has 4-bit ripple carry adder, it has full 4 adder. So that means 32-bit ripple carry adder will have 32 full adder, 32-bit adder as 32 1-bit full adder. Let's call it FA in short, full adder, which is like total 32 multiplied by 15. So this is 15, right? This is equal to 15 NAND, which comes down to be about 320 and 60, 320, 480. 480 NANDs. Now, remember, this is like a adder, but we need to do an adder subtraction circuit. That means if we go with that further down the line, here is a simplified adder subtractor circuit with the XOR through the register B. It's coming up through the register B. So this adder will have extra, if we add extra 32 more XOR on top of this, we can make a 32-bit adder subtractor. So 32-bit adder subtractor plus sum has 32-bit full adder, add circuit plus 32 XOR, which is 480 NANDs plus 32 into 4 NAND. Remember, each XOR has a 4 NAND, so 32 into 4, which is 128 plus 480 is 608. So 608 NAND. Now, so total we have 608 NAND. Each NAND has like 2 PMOS and 2 NMOS.
Remember, do you include the overflows or XOR?
This problem didn't ask for, so we are not including, but yeah, if you include, this will be one more extra, like 609 NAND.
Okay, thank you.
Sorry, no, not 609, 612, right? 1 XOR is 4 NAND, so
yeah,
the 612 NAND, but since problem didn't ask for it, so we'll just skip that. So this one is going to be like, remember this structure of NAND. This is 2 PMOS followed by 2 NMOS so this is a NAND structure. Basically, we have like 4 MOS gate, 2 PMOS, 2 NMOS. So which has like what? That means total of 4 multiplied by 608 NAND MOS transistor equals, if we multiply that, 2432 MOS. So half of them is basically NMOS, half of them is PMOS. Now each MOS is, here, let me remove that, this one. We all know that this circuit. Okay. Now each MOS has, with the given problem, 28 nanometer by 28 nanometer of footprint, which means, it implies this adder add sub will occupy 2432 multiplied by 28 multiplied by 28 nanometer square area, which is, okay, let me bring up my calculator. 2432 multiplied by 28 multiplied by 28, which is this one, 1.9 million nanometers square, which seems like a lot, but it is really not. It's really not. It's nanometer square. It's a nanometer range, right? What does it mean? This really means it occupies nanometer to micrometer is 10 to the power 3 factor. So it becomes micrometer square is 10 to the 6 factor. So it is about 1.91 micrometer square area, 1.91 micrometer square area. So that's the first problem. Second problem says how many adder we can pack into the 1 millimeter by 1 millimeter of silicon. So your area is really 1 millimeter square, which let's translate into the micrometer square, which becomes like millimeter to micrometer is a factor of 10 to the power 3. So it is 10 to the power 6, 10 to the power 6 micrometer square. So it implies that number of add sub circuit would be 10 to the power 6 micrometer square division 1.91 micrometer square. That, hey, 0.91 micrometer square, which is 10.6. Okay, 1, 2, 3, 10 to the power 6 by 1.91, which is about this much. Right? Am I correct? 10 to the power 6 by 1.91. Yeah, which is like about 500,000 if you want to say in that word, 500,000. So you can really pack like 500,000 adder onto this tiny space of 1 millimeter square, 1 millimeter by 1 millimeter silicon. Question? Okay, then let's take like 5-minute break, and after 5 minutes we'll be back. About 8:20, 21, we'll be back. Okay, let's get back with our discussion. Let me show you
Just
this.
have a question.
Yes.
Isn't it possible to implement a full adder using only 9 NAND gates?
It can be, yeah. If you optimize at very logical level, you can do that. Can you put that your derivation onto the discussion board? It's possible. Yeah, we are just discussing in terms of the given circuit, and if you just want to implement that directly with a NAND gate, we're not even talked about the optimization at this point.
Okay, thank you.
Okay, please put your derivation on the discussion. Yeah, it's possible. Like if we logically derive everything and optimize it, it can be. Okay. All right. So let's do this adder subtraction in a simulation environment. So I have an example of 4-bit adder subtractor, just like we did in our lecture. Let me share my screen. Okay. So we just did. Let's put it side by side. We started with a half adder. Half adder was this, right? 1 XOR 1 AND. So that's what we defined here, half adder 1 bit with sum and carry out bit. And then it uses inside an XOR gate and an AND gate inside that. And then we instantiate that half adder 2 times in a full adder, 1-bit full adder implementation, just like we did here with the OR gate for the final carry out bit. So this just by the connection and instantiation of the half adder. And then use that half adder to make a ripple carry adder of 4-bit. So full adder, 4 full adder, we use that just like these connections and have a 4-bit adder with an overflow, by the way. This is with the overflow. And then converted the, use that same configuration. We didn't use the RC 1-bit instantiation and make it a subtractor as well. Because of the facts, we want to redefine the overflow bit here. Like we cannot reuse the overflow from the adder circuit. So we need to, we'll just instantiated 4 times 1-bit full adder and it was driven by this XOR on the second operand with the XOR. And then overflow, we have one more XOR on top of that with overflow between the MSB and MSB minus 1, which is like just like this, CN and CN minus 1. We XOR between that 2 carry bit to make an overflow signal. And this one was instantiated in a adder subtractor test bench. We instantiate it. We drive this whole 4-bit with a AB 2 registers and another 1-bit register for sum or addition. If it is 1, then it is a subtraction. If it is 0, then it is an addition operation. Then in the test program, what we simply did, we looped between -8 to 8, -8 to 7, because 4 bits range unsigned, sorry, not unsigned, 2's complement signed notation 4-bit. Its value range is between -8 to +8. For both the operand, we have this one loop is inside another loop, and basically we set the A and B to the index value of I and J, which will loop between -8 and 7. And then each time what we did, we also toggle between sum and addition and subtraction. So first we do subtraction, 5 nanosecond after we do, first we do addition, and then after 5 nanosecond, we do subtraction on the same value of A and B. So given that, we compile, and then we pick up our test bench, simulate it, and let's see if it actually gives us the correct result logically or not. So let's add it to the wave. Okay, let's just okay, AB, SNA, overflow, radix, let's make it decimal. Okay, and simulate. Okay, it's done. Okay, let's see if it is doing correct thing or not. So we have, you see that we are toggling between addition and subtraction continuously. It's almost looking like a clock signal, but it's not. And also we have the overflow bit for some initial value. It is kind of toggling. Why? See, we started with two values, -8, -8. That means the result of addition is not going to be fit into 4-bit anymore. It's -16, which is out of range of the 4-bit result. So that's why your overflow bit is up at this point. But if we do subtraction between them, result is 0, no overflow. So the similar thing goes on. It becomes 7, and then it is addition become out of range, overflow bit is on, etc., etc. And then let's see, at some point of time, for longer time period, we will have no overflow, like between this one, like -6, -3, right? Is it -4, -3? Addition, addition is -9. Why we are getting -7? Why we are getting 7? Oh, overflow. This is overflow. Okay, that's what it is. It is overflow. But here it is not overflow. -6 -3 is -3, not overflow. -6 -2, if we add, it is -8, not overflow, and so on and so forth. So we can visually see if it is correct answer, giving a correct answer or not. We kind of know, okay, it is actually doing the correct operation there. Let's go to some positive range. Here there are a lot. No, this is -3. Okay, let's see. Yeah, I think this point of time, it's interesting. From 0 onward, we have fewer overflow at this range. So this is interesting. Let's go there. Okay, with a 0, -7, -6, etc., it's non-overflow all the way. And then suddenly we have some overflow. What it is, -8 okay, 1 minus -8, which is +9, but which is not in the range of this 4 bits, so it is overflow. So seems like it's working correct. So you see, like, even if everything inside is a logic operation and we manipulate bit to generate the arithmetic result out of the digital circuit. And that's the beauty of computer, digital computer, that nothing is arithmetic inside, everything is logic, but we still can compute mathematics out of it. Question? No question? Anyone wants to share your project 2 experience so far? Started, haven't started? Oh, everyone is silent. Means no one has started probably. Anyone has opened up the package at least and look at the guideline? Silence.
I downloaded it and opened it up and read it, but I haven't started it yet.
Okay, all right. At least some step, some positive step from Zhao. So what's your initial feeling, Jerry, about that project?
I think I have a pretty solid understanding of what to expect so far.
Okay. So do you think it can be done in time by the timeline?
Yeah, for sure.
Okay. And what kind of effort do you think you need there estimated?
What kind of effort?
Yeah, what kind of effort? Like maybe per day an hour, or maybe on the weekends straight 10 hours, 2 days, or 20 hours, 2 days. I don't know. Any initial estimation? Do you have any feeling about that?
Maybe like 5 hours of actual coding, but then like 2 days of documentation writing.
Okay. Yeah, I would be little more conservative because you will probably need to spend a lot of time in debugging. Like initial coding is maybe 5 hours. But if you step into a problem and see some instruction is not being executed correctly, at that point you can have very rough time to debug and fix. It is nothing like programming debugging. It is more like hardware debugging. You need to throw a lot of write statement inside debugging. You have to look at the waveform, digital waveform, to see what's going on inside the circuit. So please, start off front and be done with the initial implementation as soon as possible so that you can go into the test and fix cycle. That will take more time. Okay. All right then. Good night, everybody. If we don't have any more question, and then we'll see you all next week.